Hey class, Mr. Bean here. We're going to make a video. I'm here with my A1 Honors Physics class, and we're making a video here for Lab 10 Freefall, and we're going to discuss the theory behind the lab. What is that we're trying to do, and maybe show any possible calculations. All right, so here's what we have here. So from last lab, we learned that so off to the side here, we learned that the magnitude of G, this is lab number 9, the inclined plane. We learned that the magnitude of G was 9.80, we'll say meters per second squared. Okay, and for those in class here, lab 9 should be completed this week. You should be turn that in. Okay, if you didn't turn that in, some people may need to reevaluate their study habits or their social dynamics at their classroom or in their seats here. Okay, so 9.8 meters per second squared is the magnitude. Okay, all right, now. So in this case here, we're going to study a situation where we have an object. Okay, and we're going to call this situation free fall. Okay, we'll put over here free fall. Okay, so it's free fall. And what's going to happen in free fall situation is that the initial velocity is going to be 0. Okay, so if I release it, so if it's free fall, that means that G is going to be acting in this direction. Okay, G is acting in this direction, and the object here is also going to move in this direction. So the object and gravity, the acceleration due to gravity, are in the same direction. So in this case, when we do our frame of reference, so I'll go over here and put down frame of reference. Okay, frame of reference. Okay, make sure we spell that out. Frame of reference. We're going to say everything going down is going to be positive in this scenario. Free fall and G are all in the same direction, so G will take on a positive value. Okay, it's going to be positive 9.8. Okay, all right. So this is kind of like a little background here. Now for the actual lab, so we're going to take a look at Senator Square. Okay, some groups will be going out to Senator Square. Okay, and we'll take a look at the situation. Okay, Senator Square. All right. All right. Now there's this bridge. Okay, here I'll kind of go like right here, and here's Senator Square. All right. So this is this bridge, in the main bridge out here at Senator Square, and there's a brown railing. In fact, I can probably even use brown too. Let's take a look here. Yeah, here's brown. Okay, there's this brown railing. Okay, and we'll kind of go like this here, and we'll kind of okay. Brown railing here. Let's go back to black. Okay. All right. What's going to happen is that we'll kind of go like right here. I'm going to kind of draw like an imaginary straight line, reference line. Okay. This is a straight line here. Okay. Now, now since we're going vertical, instead of delta x, I'm going to introduce delta y because y is for vertical direction. Okay. So from here to here, we're going to go ahead and I'm going to put down delta y. Okay. So delta y is this vertical distance here. And it was actually measured, we actually measured it back in 2006, and it is exactly 5.2 meters. Okay, 5.2 meters. So those people in the Olympics, when they dive from the 10-meter platform, I'm very, they have my admiration because top of the railing is 5.2 meters, and they jump from twice that. That's 10. That's okay. That's too much for me. So 10 meters. Okay. All right. So what's going to happen is that this will be the same thing we use for the egg toss. Okay. So we'll have a person, let's say, like standing right here. Okay. Person standing here, and here's okay, and there's a okay. All right. Well, we'll pretend they have long. Okay. Okay. So they're going to be right here, and they're going to have this globe. Okay. So we have these mushy globes here. Okay. This is the object here, and our globes are on this desk here. Okay. We'll use that for purposes of today. Okay. They have here, and they're going to hold it. They're going to hold on to it here. Okay. We'll pretend like we're like Reed Richards from the Fantastic Four. Any Marvel fans in here? Fantastic Four. Okay, not really going to stretch your arms, but you get the idea. Okay, stretch your arm. Okay, so one person will be here. Okay, down here we'll have the lab associates. Okay, in particular, we need to have one person here that maybe that's kind of not too close, but you're kind of far away, and you're going to have a recording device. Okay, preferably I do have an iPad, one iPad here, and the other two are still charging. Apologize on that. Or use your iPhone. Okay, preferably iPhone or Android. It doesn't matter. You're going to videotape this now. Uh, So you're over here, and then then if there's some other lab partners, they may be over here, uh, might be over here, and these people here might be the timers. Okay, they may try to record it with their external timing device. Okay, but that's going to produce huge errors. Okay, timers. Okay, here will be the video person, video record. Okay, video. Okay. All right. So how this works is this person up here has to have a loud voice. Can't be squeamish or mousy like. You have to be kind of loud. You'll go like three, two, one, go. Okay. So this person will run the show here. Three, two, one, go. When it drops, you record, or you maybe want to start recording before he drops it because we can always edit it out. Okay. All right. It's going to drop here. So let's say the first moment is right here. Okay. Now, as it drops, suppose we could take a screenshot of this dropping. Are all these going to be the same distance, or is it going to be increasing? Yeah, because you're right, because it's accelerating, right? Accelerating farther, and then probably it's going to hit the ground. Okay. All right. So we're going to be accelerating as it goes down. Okay. Now down here, we have our final velocity. Okay. Right before impact. Okay. We're going to call this here. Oh, thank you, Brandon. This is called velocity uh, prior to impact. Oh, right here. Oh, yeah. Thanks. Oh, hold on. Let me hit pause real quick. All right. So when I'm at home, I have a cat that likes to jump on my lap and the screen, and I have a dog that barks and stuff. So, there's always distraction when we make videos. Okay. All right. So velocity. So this is velocity prior to impact. Prior to impact. Okay. Prior to impact. Okay. So we have velocity prior to impact. Okay. What's the initial velocity here? Zero, yeah. We're going to start from rest here, okay? And off to the side here, we know that G is going to be theoretically, G is going to be 9.8 meters per second squared. So over here, we know that G is going to be, well, if I want to, I'll put a positive here just to help us out. Positive 9.80 meters per second squared, and it's acting in this direction. All right, so these should, okay. Now, all right, is there air resistance? Yeah, there is one, but we're gonna kind of indirectly account for it. All right. So everyone understands the setup here, what's going on. Okay. All right. So we're going to scroll down a little bit here. Okay. We'll call this here calculations. Okay, calculations. Calculations. Okay. I think there's going to be at least two calculations. All right. So now, okay, what's this height? What's the starting height here? 5.2 meters. Okay. This is a timer. Okay. So this is T, right? The timer here, right? Okay. So we have initial velocity, we have the distance or displacement, and do we have this over here too, G, right? Okay. All right. So we'll go over here and we've got some calculations. Okay. So one calculation will be delta Y, right, is equal to, we're going to say VO, Y just means it's in the vertical direction. Okay. There's T, right? Plus, here we have 1/2 A T squared. Okay. Now, it's important that you did the problem set from last couple of classes because we're doing equations. Mr. Rogers, you want to wake up? Okay, sleeping is not, you can sleep after the video. Okay, all right. That's why I make it, so this is why I make the video for people who sleep. Okay, so you see why I make the video? Okay, all right. Okay, I apologize. I shouldn't be like that. Apologies, Mr. Rogers. I should not have woken you up. All right. All right. Anyways, so here we have delta Y equals YOT 1/2 AT squared. Okay, what's the initial velocity? Anybody? Zero. Good. So this is going to be zero here, right? Now, what is delta Y? Yes, good job. 5.2 meters. Excellent. Here we have 1/2. Here is A, and here is T squared. Okay. Where's our T going to come from? Oh, yeah, from who? Or how we actually get it? Is it from video? Yeah, this is from video, right? Okay, now suppose I wanted to solve for A. Okay, now we know off to the side here, we know that G is supposed to have a value of 9.8 meters per second squared. Okay, we know that. Okay, so should this A and this G be the same or close? Yeah, it should be. Yeah, it should be. Okay. So let's go ahead and solve for A. Okay. So if I solve for A, I'm going to use my advanced algebra skills. I'm going to solve for A, and it's going to be 10.4, right? 10.4 divided by, here's T, there's squared. Okay. All right. So if from the video I get the time, can I get the acceleration? Good. All right. Okay, good. All right. So we'll probably want to do like a percent error. Okay, maybe just to compare the two here. So here's percent error, right? Absolute value, okay, parentheses here. And we're going to have our experiment. This is A from the experiment minus 9.8, okay, because that's our standard, divided by 9.8, which is our standard, okay, absolute value times 100. Okay, so we should be able to do a percent error. Okay, and we did it with the AP Physics class last week, and most of the errors were under 5%. Very good, very good. With video. Without the video, 12, 13, 14% error. Okay, without video. Okay, okay, percent error. Okay, all right. So that's okay. This would be calculation number one. Okay, we need to do this here. Okay, and almost done. Calculation number two, okay, we want the velocity prior to impact. Prior to impact. Okay. All right. So now we have our sheet from last week. I think we're looking at equation number three this time. It's going to be V is equal to VOT, right? Okay. What we'll call this calculation two part A. V equals VO. Okay. Hold it. Is it? Made a mistake. He knows how I crossed it out. V is equal to VO plus it's going to be AT. Okay. So we know our acceleration. We know the time. VO is 0. So we should calculate the velocity prior to impact. Now, there's also a B calculation. There's another one. Does anyone recall what equation we might be able to use here to figure out the final velocity? Okay, give you a hint. It's either going to be 4 or 5 from last class. What's the one without time? Is that the V squared? Equation number 5. Yeah. So we have here V squared, right, is equal to VOY squared plus, right, this is going to be 2 times A delta Y. Okay. Now, what should this be here? It starts from rest. So is that 0? Okay, that is 0. All right. So do we have the acceleration from our experiment? Yeah, we calculated it. Do we have delta Y? Yeah. So this V and this V should be the same. Okay. All right. So those are our two calculations. Okay. All right. Then objectives. Okay. Almost done here. Okay. What's going to be our objectives? Okay. The objectives. Okay. All right. Okay. There's two objectives. Okay. Objective number one. Okay. Is to determine, we'll say determine the acceleration due to gravity using a toy globe. Toy globe to under, we'll say 10%. To under 10%. So objectives should be measurable. Okay, should be measurable. Okay, under 10%. Okay, all right. And then number two objective is to calculate velocity prior to impact. Velocity prior to impact. Okay. Okay. Prior to impact. Okay. Prior to impact. Okay. All right. So this will conclude our lab here. I'll go ahead and post this on YouTube, then to our Google Classroom. And then that is it. All right. Now this will be a help set us up for the egg drop. Okay, a couple questions. When we do the egg drop, do we want to have an acceleration of 9.8? Should it be close to zero? Yeah, you don't want the egg because you want the egg to survive. Like when you jump out of an airplane with a parachute, you want to live when you hit the ground. Same thing with the egg. All right, that will be it. We'll hit stop.